Hello everyone, I'm Anthony Bouchard, a PhD student under the supervision of Professor Éric Laurando at Polytechnique Montreal. And I'm going to present the work done by Dr. Mathieu Parenteau and I, called Toward a Multi-GPU Implementation of a GMRES Solver in CHAMPS. First, I'm going to present the framework used for this work and detail the solver. Then, I'm going to talk about the GPU implementation of the solver. After, I'm going to show the different performance results obtained. And finally, I'll conclude and briefly talk about the future work that is still need to be done. The code used in this work is CHAMPS, a 3D multiphysics CFD code developed at Polytechnique Montreal by the research team of Professor Éric Laurando. The code is written in Chapel and solves the Rance equations using an unstructured, mesh-based, second-order cell-centered finite volume method. The governing equations can be expressed as we see here, and we use the inexact Newton iteration to solve the system. The linear solver solves for delta W in the second equation. Solvers like Symmetric Gauss Seidel, which are often used in production codes, are not well suited for GPU. So we study the GMRES solver on GPU. This solver has the advantage of having a fast convergence when given a suitable initial solution, which can benefit unsteady simulation. Usually, the Jacobian matrix is approximated using a first-order approximation, which negatively impacts the convergence of the solver. However, the Jacobian-free version of the GMRES solver exploits the fact that only the effect of the Jacobian on a vector is needed. This prevents the need of explicitly assembling and inverting the true Jacobian. Instead, a Jacobian vector product is calculated using a finite-difference approximation, which requires another evaluation of the residuals that can be efficiently computed on GPUs. This product accurately sees the true Jacobian, enhancing the convergence properties compared to a regular GMRES solver. However, because the JFNK solver is not fully ported on GPU yet, a regular version of GMRES is presented in this work. This slide here presents the algorithm of the GMRES method, which consists of the Arnoldi modified Gram-Schmidt orthogonalization method, shown here, and followed by the least square problem. To efficiently solve the least square problem, Givens rotations are applied to the Hessenberg matrix to obtain a triangular matrix. The Givens rotations and the least square problem are both solved on the CPU given they are inexpensive. The whole algorithm is done for a certain number of iterations called the Krylov iterations, and the for loop that we see here loops over all the previous Krylov iterations done, including the present one. In the results shown later, the GMRES algorithm is split into 4 portions: the matrix vector multiplication, which is the first line of the algorithm, the Arnoldi method, which is the rest of the algorithm, and the Givens rotation, and finally the communication and synchronization part. The GPU version is programmed using NVIDIA's programming language CUDA. Only the linear algebra operations are rewritten in CUDA and linked as an external library to CHAMPS. The GPU operations are wrapped inside the sparse matrix and distributed vector objects of CHAMPS, like shown here, for the norm operation. In this example, the Kubla's dot function is in fact a C host function that in return calls a function from the Kubla's library. As a result, GPU matrix and vector objects are instantiated, and the original CPU algorithm is used directly. So the CPU code can execute both the CPU and the GPU versions of CHAMPS, like we are seeing here for a portion of the GMRES solver. If we dig deeper in the CUDA functions, for simple operations like memset operation, for example, one CUDA thread is associated per dimension of the array. For more complex operations, like the norm that we've seen earlier, the Kubla's library is used. For the coarse-grained parallelism, each zone of the grid is assigned to a task by CHAMPS and distributed over the available locals. Each of these tasks is assigned to an asynchronous CUDA stream to overlap the computations. Finally, the communication is done on the CPU side. So we copy a buffer array from the GPU to the CPU, we do the exchange, and then we copy it back to the GPU. For the multi-GPU implementation, each grid zone is assigned to a GPU. So here is an example of a matrix vector multiplication done on multiple GPUs. Each task computes the local part of the resulting vector, where the red values represent local blocks and blue values represent the off-diagonal blocks that interact with values belonging to a different task, which creates a communication point. Here we see a parallel dot product. Each task computes its dot product, and then the value are copied to the CPU and summed on the CPU side, performing a global reduction. Finally, the result is returned to every task. Now I show the different performance results obtained for this work. We used a 2 million element Cartesian grid split into 4 zones. The Euler equations are solved for a total of 10 million unknowns. The cases are run on Beluga, which is a general purpose cluster from Compute Canada. Note that because the flow solver is not ported over the GPU yet, the results shown are only for one GMRES iteration. Here we see a summary of the CPUs and GPUs on a single compute node. We have 2 Intel Xeon Gold CPUs and 4 NVIDIA V100 GPUs per node. I would like to point out that the ratio of the memory bandwidth for these two hardware is around 7, which is the speedup that we could expect if all the operations would be memory limited. Which is what we see here in the graph to your right. The CPU version uses 2 CPUs, and the speedup for 1 GPU is around 3.5, which is exactly the ratio between 2 CPUs and 1 GPU. We see that when we increase the number of Krylov iterations, the speedup stays pretty constant, and when we increase the number of GPUs, the efficiency is lowered, which is due to the communication. On the graph on your left-hand side, we see that the time per iteration increases as we increase the number of Krylov iterations. This is due to the Arnoldi orthogonalization that needs to loop over all previous iterations every time, as we see here in these pie charts. The relative time spent in the Arnoldi orthogonalization increases as we increase the number of Krylov iterations, from 30% to 64%. Now we move on to a strong scaling analysis. In these graphs, the blue line is the GMRES solver with communication, and the red line is the GMRES solver without communication. It's evident from these graphs that there is a communication or a synchronization problem between the locals, which ruins the scalability of the algorithm. If all the communication and synchronization points are removed, the GMRES solver maintains a relatively good scaling efficiency above 80%. We see that the problem comes from the communication and the synchronization part of the algorithm, which roughly represents 65% of the total time when using 2 compute nodes. This problem comes from the use of network atomics, which are working properly on CHRIS systems, but not on InfiniBand systems. The same issue is also present with our CPU implementation. So finally, here are the conclusions for this work. We obtain a speedup close to the ratio of memory bandwidth, which suggests that the operations are in fact bounded by the memory bandwidth. The Arnoldi orthogonalization is costlier as we increase the number of Krylov iterations. And finally, the use of network atomics prevents efficient scaling of the GMRES solver on InfiniBand systems. As for the future work, we'd like to work closely with Gray on a fix for this problem. We'd also like to finish porting the preconditioners, the JFNK solvers, and the rest of the flow solver over GPU so that we could compute end-to-end convergence speedup of the whole RAN solver. I would like to thank the different parties for their subventions to this project and want to thank everyone for listening to my presentation. Thank you.